thank you very much for the invitation. It's a pleasure to give a course here. So I will tell you about a phase transition which arises in 2 dimensions. I will introduce spin systems which live on ZD and in particular in Z2, and slowly tell you in this first class what the BKT phase transition is about. Maybe I will give you the plan of this course, So the first part today will be an introduction. The second part, potentially tomorrow, but maybe the introduction will go a little bit tomorrow as well. I will tell you about mathematical analysis of BKT. The third part, I will explain what I mean by domain of attraction. And what I will mean by that is what are the models that are supposed to undergo a BKT phase transition. And last course, if my timing is well designed, I will tell you about nonlinear sigma models and curvature. So since I don't quite know what is the background in the room, feel free to ask as many questions as you wish. I like things to be interactive. And I will start with the introduction by telling you about some spin systems. So let me be very organized. There will be sub-parts. The 1.1 will be spin system on ZD. So a spin system will be a map from the vertices of ZD with value in a target space. And here we'll allow ourselves to be very imaginative. So I will list many possible target spaces. The first one is a very small target space made of just 2 values, plus and minus 1. And this will be the Ising model. So in this whole blackboard, I will tell you about all the target spaces I will want to look at. The second target space we will consider will be the real numbers, and this will correspond to the Gaussian free field. Another thing we will look at will be the unit circle, and this will be the XY model. And in the second part, I will have a second model with same target space, which will be the villain model. And in some sense, this will be the crush of the course, because the BKT was first introduced for this target space here. So maybe to visualize this one, if we have D equals 2, so we are in Z2, each vertex of Z2 will carry a spin which will take its values in the unit circle S1. So this is our first realization of an XY model. I did not yet explain how these spins interact with each other. I will do so in a few minutes, but I first want to list all the possible target spaces I will be interested in. Another natural target space will be the unit sphere S2, and this is called the classical Heisenberg model. So this one is in dimension 2 is both very beautiful but also very mysterious. I will explain why. And then the list goes on. So more generally, we can view our spin systems with values in the n-1 sphere on which the group ON naturally acts, and this is called the spin ON model. So the name of the model takes as an input the symmetry group here. So this one is a generalization of the Ising case, which is n equals 1, the S1 case, which is n equals 2, the XY case, and the classical Heisenberg, which is n equals to 3. And then we can go further. Another space would be the -1,1 continuous interval. So this one was analyzed by McBrien and Spencer. And I like this one very much because in a sense it's a baby S2 model. And two other possible target space. So I could take instead of the unit circle, I could take the unit ball in R2. Maybe this one would be called B2. And this one turns out to be completely different in terms of behavior with respect to the unit circle S1. So I will also comment a little bit on this later on. And the last thing I want to list, which would be the last part of these lectures, would be what happens if we have a target space into some Riemannian surface, like a two holes Riemannian surface. So those are my models. I only talked so far about where they are defined on a ZD lattice, and more precisely in a minute in a sub-box of the ZD lattice, and they have values in one of those target spaces. So to have something interesting, I will now introduce an interaction. The spins will interact together, and the interactions will be ferromagnetic. So what this means on a picture is that if temperature is low, so we will have a temperature parameter. Temperature will be denoted T and will be 1 over beta. And usually in statistical physics, we work more often with beta than with T. When temperature is low, the interaction I will put on these spins will be such that the system will be roughly aligned. We'll want to align in one common direction. So my goal now is to define an interaction, a probability measure on this configuration, which will be such that by playing with this parameter T or with this parameter beta, by making T small, beta large, the system will want to choose a direction and stick to it more and more as T goes to 0 and beta goes to infinity. So this will be the temperature. And this will be the inverse temperature. So how do we define measures on spin systems in statistical physics? So we introduced an energy functional. It's also called an Hamiltonian. And for now on, sigma will be defined from a finite box, which I will call lambda, inside ZD and with values in S, one of those target spaces. One of those. And for notation convenience, lambda n will be a particular case of those. It will be the minus n to the power d sub-boxes of ZD. So if I have a finite box and I take any configuration like that, I want to compute, to define a notion of energy that I attach to sigma. And here there is a good news. For each of these models, except maybe the last one, they will all share the same energy functional. So for all of those, the energy functional will be, it's called the Dirichlet energy. So it's defined as the gradient of sigma, the L2 norm squared of the gradient of sigma, or in other words, and I usually take 1/2, or in other words, 1/2 sum over I neighboring j, sigma I minus sigma j, L2 norm squared. So this L2 norm here, this one depends on the target space. If it's the Ising model, then sigma I is a plus minus 1, it lives in R. If sigma I is in the unit circle, this is the L2 norm of R2. If it's the S2 sphere, R3, and so on. So I'm using the Euclidean space, which naturally embeds those target spaces. And this sum, I'm summing, so if I have this small sub-box of Z2, maybe I will do one example here. If I have an XY configuration, where everyone points in the same direction, except maybe one spin, the energy of this functional will be 3 times, so this edge, this edge, this edge, the L2 distance in R2 between this spin, so not 3 times, so this L2 distance squared plus this L2 distance squared plus this L2 distance squared. That would be the energy of this particular instance of a spin configuration on a very small sub-box of Z2. Are there questions at the moment? So I did not yet define a probability measure, I only defined an energy. And in physics, it's often natural to ask what are the argmin of H. Those are called the ground states for a reason which will be clear in a minute. So they are the configurations which minimize this energy functional. And in all the examples I gave, they are quite easy to spot. They correspond to take one point in the target space and freeze all the others to be the same.
So is there a reason why you need to embed the space into a Euclidean space too? So why you prefer the Euclidean distance over some intrinsic? So that's a good question, because when I will turn to those in the last lecture, I will in fact use an intrinsic notion of distance. But for all these very symmetric spaces that I listed before, that's the classical choice for the interaction which is used. For example, for the xy, I will give another rewriting of this with a cosine of the gradient of angles, which will be very natural. So the convenience for me at this stage is that they all share the same structure. Another reason also is that if the target space is R or Rn,
this is a quadratic form, so I will have a Gaussian vector. Yes. So the ground states, I will just picture those for the xy, but they have few degrees of freedom. They choose one direction and they stick to it. So now I'm all set to define the probability measures that I will be working with. So they are called Boltzmann measure. And they are defined as follows. So mu lambda beta of sigma will be proportional to exponential. I put it in red because this will play a key role, minus beta times the energy of sigma. So I have to be a little bit precise about what I mean by proportional here, and I will do it in two cases. I will do it first for the Ising model. Because it's a discrete spin system. And here what I mean by this proportional is that I have a finite box inside ZD, so I have a finite state space. I only have finitely many spin configuration. And to have a probability measure, I will give a weight to each of these sigma, which is proportional to exponential minus beta h of sigma. But in order to have a probability measure, I need to renormalize this weight by a positive number, which is called the partition function. And this one is defined in such a way that when I sum over all such configurations, I do get 1. So Z lambda beta of Ising is defined as the sum over all the sigma. So what is the state space? It's all minus 1 plus 1 to the power lambda. So it's an hypercube, which is getting fairly large as lambda goes to infinity, times exponential minus beta h of sigma. So this is called the partition function. And in the case of the Ising model, I will rewrite this measure in a different way. This will also be useful for xy. It's easy to check that this can also be written exponential plus beta sum over neighboring vertices of sigma I times sigma j. The Ising model is more often written in this way. And this is just because when I square this, if sigma I is plus or minus 1, I will have minus 2 times sigma I sigma j. So the minus will cancel, the 1/2 will also cancel. And then sigma I squared, whether it's plus 1 or minus 1, always gives the same number and is independent of the configuration sigma. So it means this is also proportional to this weight. And if I want to make a probability measure, the partition function is different because of this constant which appears in front. So this gives two ways of defining the Ising model. This one, we don't see the embedding in R very explicitly as in the previous one. What do I mean by proportional to in the case of a continuous target space? Here I was a little bit lousy, so if sigma takes values in the unit circle, or if I have a lambda subbox of Z2 and each vertex carries a S1 valued spin, the measure I am working with will be a measure on a continuous space. So I need to define, I have to do measure theory. I will do just 1 minute of measure theory, but I cannot give one weight to each. There are zillions of such configurations. So what I should write more precisely is that in the case of the xy model, mu lambda beta of xy. The rigorous way of defining things is that I am manipulating a measure against d sigma. And this will be proportional, and I will explain what proportional means. Exponential minus beta h of sigma, those S1 valued spins. And I will write a Radon-Nikodym derivative of this measure that I am interested in versus lambda product big lambda of d sigma, where this is the uniform measure on the unit circle. So I am defining a measure whose Radon-Nikodym derivative with respect to IID independent spins on each vertex. The Radon-Nikodym derivative fills the energy and fills the strength of this coupling parameter, which is also called this inverse temperature. So beta is very important, it's here. So now it's a bit more mathematically well defined for continuous spin systems, but I still need to tell you what the proportional to means. It means equal to 1 over a partition function, exactly like before, xy lambda beta, exponential minus beta of h sigma against this measure d sigma. And as in the Ising model, there is another rewriting of this, which is also useful. It changes the partition function by a constant. I call it z bar. And it's written as exponential plus beta sum over I neighboring j of sigma I scalar product with sigma j. So this is the scalar product. Here I still need the embedding. This is the scalar product on R2. Okay, and there is the measure lambda that I don't have room to add. So in these notations, the partition function is exactly like in the Ising model, except it is an integral over the unit circle to the power lambda of the uniform measure on all these S1 valued spaces, d sigma, times exponential minus beta over 2 sum over I neighboring j of sigma I minus sigma j L2 norm squared. So it's a well-defined integral. I am integrating on a compact space against a very simple measure, something less simple but bounded. There is no problem. Are there questions? Yes.
I have one question. Like, there the distance is measured using the L2 norm. So, sorry, when in the definition of Dirichlet energy.
Yes.
But suppose I take the S2 surface,
yes,
and if I try to measure the distance between two spin values using the arc along the great circle, will that be useful?
So your suggestion is to take, for example, S2 valued, and if this is a spin sigma at I, and this would be sigma at j, where I is next to j. So indeed, the definition I took is this distance inside the sphere, and maybe you're asking, can I use instead this one? So it's a different model, which is as ferromagnetic as the one I am working with. And I will comment sometimes that some of the proofs go through, but most proof will not go through. So for example, as far as I know, if I take the XY model, if I take this interaction, then we will prove BKT and many phenomenology. If we take this one, for a reason that I will highlight at some point in the course, I have no idea how to prove BKT for this one. So of course it holds, but in a way this shows to you that the technology we will use, they're a bit sensitive. If we modify a little bit the interaction, it could be that everything breaks. And I will point this sometimes. So for example, at some point I will state a theorem which proves a long-range order in a three-dimensional torus. So this one is proved since 1976. It works for this one, doesn't work for this one. And even for this one, if I remove one edge, so for this one it will still work, but for this one, if I remove one edge, it no longer works. So the phase transitions that I will talk about, the phenomenology that I will highlight, in some cases will be robust, but not always.
I'm sorry, I have a very simple question.
Yes.
If you remove one edge,
Yes.
then you just apply a single Radon-Lecker derivative, which is bounded, right?
Yeah, maybe you're right. This one maybe is not too brutal.
Okay.
But even then, there is no coupling, or there is no... Even then, I don't know a coupling to to try to cure this effect locally and just forget about it. So even then, I'm not fully sure. And pretty quickly, we will see why this is causing some problems. The Fourier transform of this model is not positive. And this will make many things collapsing. So that's why at the moment I'll stick to interactions which are induced by the embedding in R2 or R3 that I am picking. Okay. So if I was to write the z bar, it would be the same expression, but I would have exponential plus beta, no 2, and the scalar product. It would be basically the same integral as this one, modulo a constant that I don't want to write down. For later purposes, there is a different way of writing down the XY model, which is useful. And the way to write it down is to use the fact that the uniform measure on the unit circle can be identified with the uniform measure on 0 to pi. So I will look at the angles instead of the embedding in R2. And here I can write mu lambda beta XY measure as a collection of angles, and this one will be 1 over yet another z, lambda beta xy. And now I will have plus beta sum over I neighboring j of cosine theta I minus theta j against the product of the uniform measure on the angles, which I can write product of d theta I. And I think your suggestion, I will try to write it down, but I might fail, would be, can we work with exponential plus beta sum over I neighboring j of theta I, theta I minus theta j infimum maybe 2 pi minus theta I minus theta j. Okay, I'm not fully sure. The distance along the circle. And this is also a ferromagnetic model, but a little bit different, and most of the proofs will collapse. in a few minutes, I will show simulations to see a little bit how it looks. I will maybe make one case which is easy, and I will add one model that I forgot. The last model that I want to list will play a key role tomorrow. This is the case where the values are in Z, and this is due to the fact that the Fourier dual of the circle is equal to Z. This will play a very important role tomorrow. And when the target space is D, this is called the integer valued Gaussian free field. And it's also called the discrete Gaussian model. So among all these target spaces, there is one that I want to discuss for a few minutes, which is the easiest of all, which is the case of where the target space is R, which is called the Gaussian free field. This is the easiest of all because it's Gaussian. But if you've never seen it, this still requires a bit of a So maybe I should ask, who would be happy for me to tell you about the Gaussian free field? Very good. So the GFF, so there is a bad news. The rest will be easy, but the bad news is that R is not compact. So I cannot quite play the game I just played with Ising or XY. In those two cases, the spins were taking their values in plus minus 1 or in S1 or S2 and so on. But in R, if I try to define this partition function, I will integrate over R to the power lambda, and then I will have Lebesgue measure to the power lambda, and then in fact this partition function will be infinite. So I actually forgot something about symmetry groups, that I will start with the GFF. So what is the symmetry group of Ising? G, the symmetry group, will be plus and minus identity. So it's a very small symmetry group. And why do we have this? For any finite box in ZD, the energy of a spin configuration sigma is the same as the energy if we reverse all the spins. So the Dirichlet energy is invariant under changing the sign simultaneously of everyone. And this means that the Poynting measure of sigma is the same as the Poynting measure of minus sigma. Or in fancy words, it means that minus identity push forward measure of mu is again mu. So mu is invariant under this symmetry. If I have XY model, the symmetry group is SO2 or O2. But this one is, let me keep the fact that this one is abelian. This will play a big role later. Well, plus minus identity is also abelian. But if I have the classical Heisenberg model, the symmetry group is SO3, which is non-Abelian. And that's maybe one of the sources, one of the main reasons why this system is much more mysterious in dimension 2. And for my Gaussian free field, what is the symmetry group? Before I define the measure, the symmetry group is abelian. This is nothing but R. So for the GFF, the natural symmetry group is R because H of sigma, so in the case of the Gaussian free field, we don't use the notation sigma from ZD to R, but rather we use the field notation phi from ZD to R. So it is the same model, but usually we work with the Gaussian free field with this notation. And h of phi is the same as h of phi plus any constant c for any c in R. So that's why the a priori symmetry group of GFF is given by this additive group here. But we have the same issue as with a Lebesgue measure. There is no probability measure on R, which is invariant by translation. So in fact, we don't have a very nice Gaussian free field model on a lambda box. To have a well-defined measure, we need to break this symmetry. And to break this symmetry, we will need to equip the boundary with boundary conditions. So to define a proper measure, to define a proper probability measure, we need to break the symmetry by imposing boundary condition, and the boundary condition that I will impose will be Dirichlet boundary conditions. So what do I mean by this? So I will take lambda, a finite box in ZD. I will only draw things in Z2. And I will force the boundary values to be equal to 0. So let me take a finite box of ZD with here D equals 2. There is no GFF, no Gaussian free field if I don't apply some boundary conditions. So let me put 0 everywhere outside this box. And now I want to define a probability measure in the middle, which is such that lambda beta GFF, this means Dirichlet boundary condition outside of d phi is proportional to exponential minus beta over 2 some I next to j in the full Z2. Maybe I don't have the best way to take into account boundary condition. And now I have phi I minus phi j squared. I impose that for all the points outside of lambda, phi is equal to 0. So everywhere here, those are not very needed because there is a Markov property. It only fills the boundary condition just outside the box. And then inside, I have a Lebesgue measure on R, d phi. So if I want to make a simulation of what this looks, I will just rotate a little bit this piece of Z2. So this is my same piece of a sub-box of Z2. I have zero boundary condition everywhere, so I have, if you wish, a flat field. The field is flat outside of this box, and on this axis, I will picture what the Gaussian free field looks in the middle of this box. So it should look like a random function. A two-dimensional one, so okay, maybe in 2 minutes I will try to find a picture on the web, but it's a random surface on top of this two-dimensional box in Z2. And the point is that the partition function now is well defined thanks to this symmetry breaking on the boundary. Maybe I can do the exercise if lambda is just 1 point. If I have 1 point in Z2, so I have 4, 0 around this point, and I try to put a random variable whose probability measure is just on this point, is proportional to exponential minus beta over 2. I have 4 interactions, so I have 4 times phi squared d phi. So, okay, I took a bit of a, I only have 1 point, but here I have a Gaussian random variable, and I can compute the variance of this one. I let you do the exercise with a bigger box. And what I claim is that whatever finite box you are working with, the integral of the partition function is always finite. And what we are working with is just a Gaussian vector of finite dimension. So this is now, this is a well-defined Gaussian vector on a finite dimensional vector space. What is the dimension? It's the number of points I have inside my box lambda inside ZD. So I will just slightly rewrite these things to see some probability coming in. Now that I have a well-defined Gaussian vector, I will highlight what is a covariance matrix. So as we would do in analysis, we can do a discrete integration by part to show that mu lambda beta GFF with zero boundary condition outside. This is proportional to exponential minus beta over 2 scalar product of phi with minus Laplacian of phi. So this Laplacian, as in analysis, there is a Neumann Laplacian, there is a Dirichlet Laplacian, and there are many others. This one would be the Dirichlet Laplacian, so that it takes into account the interaction with the zero boundary condition. So maybe I will not do it very consistently, but this is the Dirichlet Laplacian. So if I do this, I recognize the covariance matrix, this Gaussian vector, as covariance matrix. So it will be the inverse of the Dirichlet Laplacian. And there is also beta here, which plays the following role. If I don't mess it up, it's 1 over beta times the inverse Laplacian. So how to visualize, so what this means, probabilistically, it tells us everything about this random function that I have drawn here. It says that if I take this box, maybe let me take a larger box. If I want to know what is the covariance between this x and this y, the covariance of phi at x and phi at y will be 1 over beta inverse Laplacian at x and y. And this corresponds to a green function. The inverse of the Laplacian is the green function. So it will be the green function of the simple random walk in lambda killed on the boundary, starting at x and counting the number of visits at y. So if I want to understand this field, I can start a random walk here. And I count how many times I visit y. Until I decide to exit the box and hit the Dirichlet boundary condition. So in other words, I claim this example is simple in the sense that it is Gaussian. But since it is Gaussian, I can compute everything, which if you've never seen this computation, it goes way too fast. But the moral of the story is that it's a completely solvable model. I can understand what is the variance of the field at one point, what is the covariance, only by playing with simple random walks. And this spot, so maybe this is the first time I can do a symmetry breaking. So this is my 1.2 part of the introduction, which is symmetry breaking. If we take the Gaussian free field, which is the most solvable of all these models, so the GFF does not break the symmetry in dimension d equals 1 and d equals 2. It does break the symmetry in dimension d greater or equal to 3. So for the GFF, there is a difference between low dimensions 1 and 2 and high dimensions 3, 4, and so on. And how do we spot this? I will do the computation in dimension 2. If I take a big box, an n by n box, so just to recall the notation, lambda n is minus nn to the power 2 inside Z2 for d equals 2. And if I take this huge box with n very large, and I have 0 boundary condition here, if I play the same game as I did here, I can ask myself, what is the amount of fluctuation for the GFF in the middle of this box, in 0? And so the variance of this GFF phi, so the variance for the GFF in the box lambda n at inverse temperature beta of phi at 0. This is the green function in the middle of the box divided by beta. So we see here that beta doesn't play a very big role, it's just a scaling. So by varying the inverse temperature beta, it will only have the effect of scaling the GFF. There will be no phase transition, nothing. But what is important is that the green function fills the dimension. So if D is in 1 and 2, the recurrence of the simple random walk implies that the green function blows up, and we can be more quantitative. If D equals 1, it blows up like n, and if D equals 2, it blows up like log of n. And in fact, this logarithm here will play an important role even for BKT later, for this Berezinskii-Kosterlitz-Thouless. So it blows up, so it means in dimension 2, this random surface fluctuates, and typically in the middle of the box, we see fluctuations of size. We see Gaussian fluctuations, but they are of size square root of log n, because the variance is log n. So this diverges, and we say that the GFF is delocalized. And in particular, if I want to take an infinite volume limit, if I want to let lambda n span the whole Z2 lattice, the measure will not stabilize, it will fluctuate more and more, and it will not converge to a well-defined measure. Only a natural measure is preserved in terms of the gradient of the field, but the height of the field itself diverges. So it's in this sense that we don't break the symmetry, because in the end we have a measure which is only defined modulo vertical translation, and which, because we take modulo, keeps preserving this symmetry group. So it's a little bit... this one is semi-satisfying, but if D is equal to 3 or more, there we can really say that we break the symmetry in the following sense. So if D is equal to 3 or D greater or equal to 3 works also. If I take a GFF in the n by n box of Z3, and I monitor what is the fluctuation in the middle of this box, the variance in this three-dimensional n by n box at inverse temperature beta of the GFF in the middle will be the green function in 3 dimensions in this box at 0, 0 divided by beta. And now the great difference is the transience of the walk. This converges to a limit when n goes to infinity, which is the well-defined green function on the whole Z3 lattice at the point 0, 0 divided by beta. So what this means is that at least the fluctuation on a 3-dimensional lattice stabilizes as the boundary condition flies away. So this means that there is a chance to have a well-defined spin system on the whole Z3 lattice, and in fact it is the case. I will not prove it. It's not very difficult. So maybe I will just write mu lambda n in D equals 3 inverse temperature GFF. This measure on a finite piece of Z3 converges in law as n goes to infinity to a mu GFF on the whole Z3 lattice at inverse temperature beta. And what is important here is that I need to have zero boundary conditions, otherwise this measure is not well defined. And this boundary condition is still there in the infinite volume limit. It remembers what was the boundary condition in the infinite volume limit. And this is why I claim there is symmetry breaking here. The way we play with the boundary condition still impacts what the system is doing in the bulk of the lattice. So are there any questions? I'm happy to stop for a while and I will show you simulations of these spin systems. Good.
May I ask a question?
Yes.
So if instead of looking at variance, I will look just at the mean value of phi at 0.
At the mean value?
Of phi at 0.
Yes.
Will I see any difference between d more or equal than 3 and d below 3?
Yes, so good question. So, right, so indeed in those two blackboards I only mentioned what the variance is doing, but I didn't tell you about the mean. So the mean will fill the boundary condition. If I have zero boundary condition, the law of phi is the same as the law of minus phi. There is the same kind of symmetry as for the Ising model. And so a Gaussian which has this symmetry needs to have zero mean. So this will be true for both dimension 2 or dimension 3. The way to spot the symmetry breaking is that if now I pick boundary conditions which are 5.5, the variance will not be affected, but the mean will be 5.5 even as the boundary condition goes to infinity. So in this sense, the system remembers the boundary conditions because the mean keeps track of what is going on at infinity. So indeed, the mean is important because that's the observable which spots the symmetry breaking. So thank you for the... Okay, so this is a simulation of a... So I'm sorry for the Ising experts. I will soon go to BKT, but so this is a 100 by 100 lattice. So this is d equals 2. Thank you. Sorry. So this is d equals 2. This is a website by Demidov that I always use for my teaching. So it's a 1000 by 1000. So this is my lambda box of the beginning of this class. Inside Z2, there are no three-dimensional picture. And this is not beta, but this is T. So I will always use beta equals 1 over T, but this is temperature, and this one is the critical one. And what I often like to do is to dynamically change the temperature and to make it suddenly, abruptly, very, very cold. So if we do this, the two phases, the plus and the minus phases, they are fighting with each other. They remove the unpleasant color, black here, white here, inside the hulls, and then they fight along those interfaces. And this is a very beautiful world, but this is not what we will do in this course. This would be interplay between probability theory and PD. So maybe Thierry would be more in business here. But what happens is that as we go close to this black dot, that's the critical point, and this is defined as the point such that above there is just one infinite volume limit, there is no symmetry breaking. All mergers that live on the whole of Z2 at those temperature T, those beta, there's just one, it forgets whatever you built on the boundary. At the moment you go here, the phase transition is continuous. This is a theorem of, I guess, the 80s. Maybe even before. No, Onsager knew it was continuous, so it's even way before. So at this moment, there is only one infinite volume limit, but this infinite volume limit is very interesting. It doesn't really know where to go. It hesitates. and it creates very nice fractal curve between the minus and the plus. If I had a nice website with a Z3 simulation, you would see that at the critical point you would also have continuity. Two phases would be robust, but this would be a recent theorem by Eisenman, Dumil-Copin, and Sidoravicius from 2013. That Ising model on Z3 has a continuous phase transition. And if you go to this, if I don't want to do the PD world, I have something I can click on the top here, which is cooled, which starts the initial configuration with all pluses, all black, and then run the Markov chain dynamics to see, so we don't see anything here, so let me put something a little bit closer to the critical point. So that's another way to spot symmetry breaking. It means that I broke the symmetry with the initial condition, but now the Markov chain will take ages before going to the other phase, which would be the white phase. So I will spend 5 minutes or maybe 10 to very quickly prove this. So sorry for the experts, or I will ask if you want me to do it rather. And the point of those 10 minutes will be to highlight that this proof will not work for continuous spin systems. So in this same website, there is a simulation of the XY model. Okay, I did not introduce this, maybe I should have. This is a bit like an Ising model, but with 3 colors. So the target space, it should have been in my list because it's a famous model, so it's a bit a shame I didn't include it. It's my fault. So the state space would be blue, green, and blue, green, and red. And I can define, I can embed it in R2 if I want to keep the structure as I had. And with those 3 colors, as I play with the temperature, there is also a critical point. And the proof I will do for Ising works equally well for this model. It shows that there is symmetry breaking if I choose blue, for example. I break the symmetry with blue. As I go closer and closer to the critical point, the blue remains, and it will take exponential of the volume time in the Markov chain to turn maybe to red. So there are different ways to define symmetry breaking. Either you equip the boundary with blue and you let blue go to infinity and you ask yourself how does the system react to this, or you have a dynamic way to speak of symmetry breaking. And the last simulation I want to show is the XY. So that's an XY model. So here, let me do the high temperature XY. So this is a 1000 by 1000 sublattice of Z2. And now each point, each pixel, is one S1 valued spin, which is colored in a periodic way. So I always use this simulation because they're quite beautiful. So there is a periodic way of affecting color depending on the angle. And at high temperatures, very disordered, we'll see that there is exponential decay of correlation between this point and a point far away from it. If I suddenly freeze things, then maybe this is too much. So I could also break the symmetry. If we do this, as opposed to the Ising model, I will prove a theorem maybe today that the XY model will never break the symmetry. So eventually it will forget what is going on. So I think there is a bit of a, oops, sorry, should have removed this. Sorry about that. So I think there is a bit of a defect in the simulation because it looks periodic and it should not. It should be reversible. So I will prove to you that the XY model, and in fact all these S2 valued Sn minus 1 when n is greater or equal to 2, and these ball values, all of those they have a continuous symmetry built in, and they cannot order in dimension 2. And this is a celebrated theorem by Mermin and Wagner, which is 10 years before the, or a bit less, 10 years before the discovery of the BKT phase transition. But to appreciate BKT, we'll need to first appreciate the lack of long-range ordering in dimension 2. So we will need to appreciate the difference between Ising plus minus 1 valued and XY, which is this S1 valued spin system. Are there questions on the simulations or the models? Don't hesitate, I have no clue if I'm going too slowly or too fast. Okay, good. So, the Gaussian free field I did not prepare, but I can Google. Yes, it will. I think it will work well, very well. So this is, I think, Ellen Powell, because I use it a lot. So I don't know how to make it bigger. Is it big enough? Or? So this is my lambda subset of Z2, and this is what I tried to sketch before. But this is an actual simulation. So you see that in 2D, this is very, very erratic, and what I proved to you is that the variance in the middle blows up as the magnitude of this sublattice goes to infinity. So those are this is a Wikipedia one, I don't know who did it. I think this could be Scott Sheffield, this looks like the style. They all represent the same. This one may be slightly interesting because there is a boundary condition which is not Dirichlet. You can impose other boundary conditions and try to see how the system reacts to those. I will close the computer forever now, so if you have a question. So the next two items I want to do is why do we have symmetry breaking for Ising in dimension 2 and higher? And then why we don't have any such symmetry breaking for XY model and continuous symmetry spin systems. So do you want me to do the Ising case? I'm happy to if you want, but if you've all seen it, they shouldn't do it. It's called the Peierls argument. No? You want me to do? Okay, I will do. So I will do it quickly, and if you have any question, you can ask me at the end. So what I will shortly sketch is why, when we have a n by n, so let me take this n by n box in Z2, and I want to prove to you that the Ising model will remember a way to break the symmetry on the boundary. So I will equip the boundary with plus. And I want to show to you that if beta is large enough, which means if the temperature T is small enough, then uniformly in the size of the system, any point in the bulk, for example 0, will remember what the boundary, how did we prepare the boundary. So the only thing I need to prove to spot a symmetry breaking is to compute what is the probability with plus boundary condition for Ising. I will not keep track of Ising here. That the spin in a point, say the middle point, but the proof would also work for this point far from the boundary, that this point is in the other color. If I can show that this is less than 1/4 uniformly in the size of the system, this means the Bernoulli coin that I have in the middle is not a balanced Bernoulli coin, and therefore there is symmetry breaking. So I need to upper bound this in a good enough way to have something small strictly smaller than 1/2 uniformly in N. So this, the first claim I say is that this is less than the probability that there exists an interface gamma which is such that gamma has pluses outside and minuses inside. So gamma needs to surround 0. It could go all the way to the boundary. That's allowed. So something like that. And it has pluses outside, including in the boundary condition. And it has minuses everywhere inside. And 0 is here. If 0 has a minus spin, it needs to be the case that you can find such an interface gamma. It is not an equality, because if you had two such interfaces, you would go from plus to minus and back to plus. So it's only an upper bound. But to spot symmetry breaking, that's enough. So by union bound, so maybe let me rewrite this as a union over gamma of the event that gamma is of this type. And by union bound, this is less than the sum over all such interfaces gamma of the probability that the spin configuration is consistent with gamma. By consistent, I mean the sigma field of spins has minuses inside gamma and pluses outside. So now I have to upper bound for each given gamma. I have to upper bound what is the probability that an Ising spin configuration sigma is compatible with this fixed gamma. And that's, I think, where Peyer's argument, that's the most important step. So let me write this sum over gamma. In the numerator, I will sum over all the Ising configurations that are compatible with this. And here I will remove the partition function. I don't need those. Exponential beta sum over I neighboring j of sigma I sigma j divided by sum over sigma exponential beta sum I neighboring j sigma I sigma j. So one upper bound I could do is that the numerator is less than the denominator, because I have less things on the numerator. But that's not very good, because I still have the sum over gamma. So Peyer's found a way to gain something at fixed gamma here, and he noticed the following. He noticed that if, let me not go all the way to the boundary, oh, well, I could. If this is gamma, and if sigma is compatible with gamma, so it has spins in the middle that are minus, what Peyer's did is that he flipped all the spins inside gamma. So he took all those spins that are compatible with gamma and let minus sigma inside gamma. So it means now those have to be plus. And at distance more than 1 from gamma, it can be anything. And let me call this map sigma gives sigma gamma bar. My notation are not very good, but this is an involution which depends on gamma. If I apply it again, I go back to sigma. And if I use this trick, I will rewrite the numerator as sum over gamma bar, such that sigma before or after the gamma bar is compatible with gamma, exponential beta sum over sigma I bar, sigma j bar. But there is the energy of sigma bar is much lower than the energy of sigma. It has the same internal energy here, same external energy, but the sigma bar doesn't pay the same thing along gamma as the initial sigma. And the difference is easily seen to be exponential 2 beta number of edges between the plus and the minuses. Why? Because before flipping, I will pay for each such edge, I will pay exponential minus beta times 1. And after the flip, I am collecting exponential plus beta times 1. So this sigma bar is much more likely, much more comfortable than the initial sigma. And the difference between these two is given by this. And I still have the same denominator, which is sum over all sigma. And now I can use what I said before. I am summing over less configurations on the numerator than on the denominator. So this whole thing here is less than 1. So I ended up with an upper bound. I still lose something. I kept losing more and more along the computation, but it's still good enough. Sum over all the interfaces that go around 0, possibly all the way to the boundary, exponential minus 2 beta times the perimeter of gamma. And this, by some not too difficult combinatorics, can be made less than 1/4 uniformly in n if beta is sufficiently big. For example, 10 will be far enough if we are in dimension 2. So here there is some combinatorics involved, but it's not very difficult. It just, one way to do it is to count all the interfaces that surround 0, to split the sum depending on where does the interface start, and then use the fact that if you start k steps on the right, the interface needs to be at least 2k long, and an interface starting here, at each step it has at most 3 steps ahead. So the number of interfaces is exponentially big in the number of steps, but this is an exponential cost in the number of steps. So if beta beats this entropy, you're in good enough shape. So it's a terrible sketch if you've never seen it. But it's a combination of it's this energy analysis here and this entropy analysis here, which counts the number of interfaces. So this is called Peierls argument. This is used nearly everywhere in statistical physics. It goes back to 1936, and it's a beautiful argument. So it's beautiful, but for xy it fails. For xy or classical Heisenberg, maybe just to change mood, I will draw with classical Heisenberg. So Peierls does not work for spin systems with continuous symmetry. And in fact, we've already seen an example. We've already seen that the GFF, the Gaussian free field in dimension d equals 2, we've seen that it doesn't remember the value that we have at the boundary. So you may try to do Peierls argument to remember the average value of the field in the bulk, and you will see that it collapses. It also collapses for xy, S2 valued, and so on. And why that? If I take a S2 valued spin system, I could try to break the symmetry by equipping the boundary condition with north everywhere. And then in a two-dimensional box, or even in ZD, the Peierls argument will never work whatever the dimension is. It doesn't mean long-range order could be correct in large enough dimension. I will comment this later. But if you want to ask yourself what's the probability that the spin in the middle is in the lower hemisphere, if you don't have symmetry breaking as n goes to infinity, as the size of your box goes to infinity, this should converge to 1/2. But if there is symmetry breaking, maybe this would be less than 1/4 uniformly in the size of the domain as we had here. If we want to apply Peierls argument, the beginning of the proof is the same. Maybe I will find a gamma in dimension 2 or a surface in dimension 3, which will have upper hemisphere values on the exterior and lower hemisphere, so south hemisphere inside, north hemisphere outside. This part of the argument over here still works. What doesn't work is the moment where we use the spin flip symmetry of Peierls. So it would correspond to taking all the spins inside and changing hemisphere. So we revert the hemisphere in which we are. So if we do this, we erase this interface as we did here. We preserve the internal energy, we preserve the external energy. But the sad thing here is that what do we collect along the interface? We collect much less than we did collect over here. Over there, it was very comfortable because we were comparing what is the cost between this before inversion and after inversion, which was this. This was much more comfortable than that. And the difference of energy was exponential minus 2 beta. If beta is big, this is a very small number. Now, when I do the switch, the inversion, it could be that inside, the point is very close to the equator, and outside, the point is very close, but in the north hemisphere, to the equator. At the moment I will flip inside, the energy will be a bit more comfortable, but certainly not exponential minus 2 beta. It will depend on the distance, in fact, not only to the equator, but also to the sigma I here and sigma j here. But I don't have a comfortable upper bound like exponential minus 2 beta on the energy gain that I have by doing this inversion. And because of this, the argument completely collapses even in dimension 18. And it's still an open problem today to find such a type of Peierls argument to work in dimension d equals 3 or higher, where it is known by other means that there is symmetry breaking. In dimension d equals 2, this doesn't work for a good reason, that it's wrong. There is no symmetry breaking for x, y, or classical Heisenberg, or any of those that I discussed so far. So what I will do now, unless there are questions, I will prove that there is no symmetry breaking in dimension 2. And here I hesitated a little bit. I thought I would bypass this proof, but then when I read it again, I thought the proof would please Thierry. Thierry Bodino, not Thierry Lévy. I mean, maybe, but there is an inequality which I've seen several times in your papers, Thierry, so it's for you. So we'll prove Mermin-Wagner's theorem by playing with the total variation distance and inequality you like. I will also do it a little bit quickly, but I will convey the main ideas. So So 1.3, no symmetry breaking. In D equals 2, for those, for spin systems with continuous symmetry. So the important thing here is dimension 2. I will explain why the proof collapses in dimension 3 and higher, and also continuous symmetry. We don't need abelian symmetry here. Abelian will be for the BKT phenomenology. So, so maybe I can state a more precise theorem, which is due to Mermin and Wagner in the 60s, and which says the following: for every n greater or equal to 2, so the n is for the spin-O(n) model which have Sn minus 1 target space. If mu is an infinite volume limit of spin-O(n), so this works for xy, classical Heisenberg, and so on. So maybe in parentheses, such infinite volume limits do exist because Sn minus 1 is compact. So what I mean by that is that if I have a finite box of Z2 and I have spin in S2 that are interacting in the way that I described before, as my box lambda grows larger and larger to eventually cover the whole Z2, it's not clear at all that mu lambda n beta converges in law to an infinite volume measure Z2 beta. That's not clear. But since those spaces are compact, it's by compactness, it's easy to show that there exists subsequential scaling limits which converges to possibly many infinite volume limits. So the question of existence is easy. The question of uniqueness is much, much harder. But Mermin-Wagner doesn't care about uniqueness. What it tells you is that any such infinite volume limit is rotationally invariant. Then mu is rotationally invariant. So it puts a huge constraint on those possible limits. There could be several, but they have to be invariant under the action of a global symmetry. So what this means is that for any R rotation in SON, the push forward of the infinite volume measure that we look at is the same as mu. And what I understand by this push forward measure is just the following experiment. I sample an infinite volume limit of xy. So in the whole Z2 lattice. And if my rotation in SO2 is e to the I theta, the way I act on this spin field is that everywhere on the Z2 lattice, I rotate by the angle theta my spins. Okay, so it's a global, it's not like in Young-Mills for the last row here where you have much bigger symmetry group. It's a global rotation which is applied the same way everywhere on the Z2 lattice. And Mermin-Wagner tells you that any limiting measure needs to satisfy this invariance under rotation. This is not the rotational invariance of Fk, which is popular these days, where they rotate the lattice. I'm not rotating the lattice here. So how do we prove this? The idea is as follows. So proof. So let's view mu as a limit as k goes to infinity of mu lambda nk beta, possibly with some boundary condition outside of this nk box. So now I have a measure on the full Z2 lattice. Let me take n very large. I look at the n by n box lambda n. And what I will do, I will sample, according to this measure mu, the spins outside this n by n box. So this could be very complicated. I have no control on what those are. This is a very... This could be anything. If beta is large, maybe this would be more something like that. More aligned than what I did here, but it's a random configuration of angles on all the vertices outside this n by n box. So yellow x in the outer of lambda n, they are sampled according to mu. And what I want to prove to you now is that what I see in a finite window of size r here, what I see here is in total variation distance more or less the same as if I rotate everything that I see in the middle by an angle theta. And to make my life slightly easier, but this is really a tiny simplification, I will make r equals 1, and I will just try to rotate what happens in this spin in the very middle. So I will prove to you rotational invariance for the middle point here. I want to prove to you that this point is sampled according to the uniform measure on the unit circle S1. Whatever the boundary condition is. So of course this will be wrong at finite n, but as I let n goes to infinity, I will converge to the uniform measure on S1. So how to prove this? So we will use a spin wave and to me a spin wave will be a function. It will be a scalar, a real valued function psi, which will satisfy the following. Psi at 0 will be equal to pi. Psi at the boundary of size n will be equal to 0. So far I can find such functions. It's not very difficult to satisfy this. But the main ingredient is that I want the Dirichlet energy of psi, namely the sum over I neighboring j in lambda n of psi I minus psi j squared to be small. Small as n goes to infinity. So I want to find a function which is costing a small amount of energy and which is inverting the direction. So I will do this, but then I can apply it for any angle theta between 0 and 2 pi. So if I was to make a drawing, a spin wave will look like that. 0 angle on the outside. Let me picture e to the I psi x in lambda n. I want to have this target point here. And in between, I want to interpolate as slowly as I can. So Ivan Velenik in his lectures notes has much better drawings than this. But we want to find a psi which interpolates from 0 to pi in such a way that it pays little Dirichlet energy, little sum of gradient squared in this box. So I will first build one, and once I will have such a spin wave, I will prove this statement here. So just to appreciate, let me make a first attempt for the green function, the harmonic analysis, and all this. What I will do is completely suboptimal. But the first attempt will be even less optimal. So what we could try to do is to have a function which is constant on the L infinity boxes. And maybe the most natural guess is to have a linear interpolation from 0 to pi. So maybe I have a... Okay, for the moment I will do the reverse job. It's slightly easier to write down for me, and at the end of the day I can just flip everything. So I can do 0 here. I want to go to pi at distance n, so maybe here I can do 1 over n times pi. The second square I can do 2 pi over n. At the I square I can do I pi over n, and by the end of the day I will reach the boundary condition I want. So if I do a cut of this, my function is something like that. It interpolates linearly from 0 to pi at distance n. So this is not a good choice. This would work in dimension 1, but it doesn't work in dimension 2. The Dirichlet energy of this psi up to constant, what is this? I will only take into account those gradients because those ones are equal to 0 anyway. So for each I between I and n, I have roughly 4 I points around, and each of those has a gradient of 1 over n, or maybe pi divided by n square. And if I compute this, sum over I is of order n squared. I have an n squared here. So this is up to constant 1, which does not decay to 0 as n goes to infinity. So this is not what I call the spin wave. This will not be sufficient for what we want to do later. So I will make something which will be a bit better. So a better choice is to take into account that far from 0, I have many points along this square of size I. So maybe it's a better idea to, I don't quite know how to draw, but to do something which the gradient still needs to go to 0 everywhere, but it needs to be as flat as possible close to the boundary, because I have many points to deal with here, So I will give you a nearly optimal choice. From harmonic analysis viewpoint, this would be easily explained, but I don't want to go into this. This would have to do, maybe I can say it in words. The best possible spin wave here is nothing but the harmonic extension, the harmonic function, which is extending 0 here and pi on the boundary. But this one in the square, you can play with random walk, but it's not super explicit.
So here you're really using the argument, not embedding the S1 into the R2.
Yes, I think you are right. So what I will prove here will work for all the models we like your suggestion, this will work very well, for example. So I don't use the embedding here. This is very robust. And it works for S2, for the Polyakov, it works for all the nice models, but what it will prove is this interesting fact that there is no symmetry breaking. So in principle, there is no phase transition. The BKT phenomenology will say that for some of those models, despite the lack of symmetry breaking, there will be a phase transition. This will be more subtle and this will be more sensitive to the interaction we are working with. But indeed, this will work. I mean, maybe my proof, I would need to struggle more with my Taylor expansion, but this will work very well. So I don't want to play with the harmonic extension because, I mean, this would be the optimal choice, but a nearly optimal choice, it's optimal in the speed of convergence, but not in the multiplicative constant in front, would be to design psi on the L infinity box at distance I to be 1 plus 1/2 plus 1 over I divided by log n times pi. Okay, so maybe at the end of the day it's not quite pi almost, but don't be too picky with me. So this almost achieves what we want. The Dirichlet energy of this psi up to constant. So I still have order I points on the boundary of this square. But now what is the gradient? The gradient is 1 over log n times this up to I plus 1 minus this up to I. So maybe 1 over I plus 1 here, that would be the gradient. But the Dirichlet energy is about summing gradient squared, fortunately for me. So up to constant, that's the Dirichlet energy of this suggestion here. And now if I compute, this is much better than before because this is 1 over log n squared times up to constant, sum from I equals 1 to n of 1 over I, which itself is also a log n, but there is a square here. So up to constant, this is 1 over log n. So we found a spin wave which has the correct boundary condition and does not require too much energy to go from distance n to distance 0. So I know IHS there is coffee at 4, so I need to speed up. So what do we do with this spin wave? Maybe I will make a drawing. In Mermin-Wagner's theorem, we are manipulating this infinite volume measure mu, which has this very complicated boundary condition a priori. So what I want to do, if I would want to do the scale r, I would need to build a spin wave which would start at lambda r and then go to distance n, which would be more or less what I did, but I only did r equals 1, so I want to say that I want to rotate the spin in the middle in an efficient way. So what I will do, I will compare the following two measures. The first one, I will fill all the spins in this n by n box. So there is a lattice here. It's very badly drawn, but all these arrows are on a piece of lattice. And maybe in the middle, I have something like that. So this is a sampling of my true infinite volume measure mu. And I will compare this true sampling with a fake sampling as follows. I will take this spin field and I will act on this spin field with the spin wave that I have here. How will I act? I will rotate my spins here. So I will, maybe in notations, I will Can I erase this? So I want to show that r theta applied to mu is equal to mu. Okay, so my pi was not a very good choice, but I don't know why I had pi everywhere. Okay, let me put alpha times pi. It's a terrible choice, but so I rotate by alpha times pi. So I will use the following transformation: T alpha times psi acting on a field of angle theta x, x in lambda n, will be equal to the new configuration of angle theta x plus alpha times psi at x, x in lambda n. So this is a transformation acting on my spin system. I will try to draw what this is. It barely doesn't move here. But in the bulk of the system, in the middle here, maybe this starts moving a lot. So the amount of angle we have is alpha times psi at the point where we are. And at the end of the day, in the middle here, we have exact rotation alpha times pi. Okay, so I take this true infinite volume measure and I twist it in this rather subtle way, more and more as I go in the middle of the system, but barely not at the boundary of lambda n. And the game, the goal, is to show that if I act on this spin system with this transformation, I obtain a new field of angles which is basically the same in law as the initial one. How do I make sense of this? I will measure the distance between the true measure and the spin-waved measure with a strong notion of distance. So I will compare mu lambda n beta, and there is this theta 0 which is complicated, which is sampled according to the infinite volume measure. And I will compare it with the push forward under this map of mu lambda n beta theta 0 in total variation distance. So this is maybe one of the strongest possible sense of comparison between measures. If you've never seen it, I'm happy to tell you over the coffee what this is, but this is a very strong notion. It's a maybe I will give a counterexample. It's so strong that the total variation distance of the Dirac point mass minus the Dirac point mass at epsilon for measures on the real line, this distance is 1. Even as epsilon goes to 0, epsilon non-zero. So it's very, very strong. It's very sensitive. And I want to show that this goes to 0 as n goes to infinity, where the psi does depend on n. It did not in my notations, maybe it should, but the spin wave fills the space we have around us. And the key lemma, which I think Thierry is using often, so is a Pinsker inequality. Okay. So Pinsker inequality tells us that for those statistical physics Gibbs type measures, this is a little bit hard to work with, but there is something more suitable for us. If I have two probability measures on a target space or on any measurable space, the total variation distance squared is less than twice the relative entropy. So I will recall what the relative entropy is. So this is very easy to prove. So this basically uses calculus. So how does x log x look close to x equals 1? So of course it's not sufficient for a proof, but just to tell you that there is nothing mysterious behind this inequality. The only thing I should emphasize is what is the relative entropy. So definition, h of mu with respect to u, and here I have 50% chance of collapsing myself. So this is expectation of log d mu. So this Radon-Nikodym derivative, but in the measure mu. And I claim, if I have 50% chance, that this is positive by Jensen. I think it is. I did it yesterday, it should be fine. So it's a very easy definition, but it has one huge drawback. We will see that this is very convenient for Gibbs type measures, but this one is different from h mu relative to mu. So this is a distance that I did not define. It's a very strong distance. It measures how a probability measure is close to another one. It's symmetric as distances like to be. This is also a measure of distance, but is not itself a distance. Yet the fact we are averaging the log of the Radon-Nikodym derivative is super convenient for us because all Radon-Nikodym derivatives have the shape exponential of some energy. So the relative entropy will remove the exponential and will work directly with energies. So I only need to compute relative entropy of mu. So I need to do it the right way. I will look at the relative entropy of mu lambda n beta relative to the more complicated one, which is alpha psi push forward of mu lambda n beta. If this has a small upper bound as n goes to infinity, we are done. So let me compute what this is. This is the expectation under mu, under this one. This is why I use this one on the right. So this is the expectation under mu lambda n beta theta 0 of the log of the Radon-Nikodym derivative. And this log is simple here, so maybe I will still keep the log. I have exponential beta sum I neighboring j of cosine theta I minus theta j divided by E beta sum over I neighboring j of cosine theta I plus alpha psi I minus theta j plus alpha psi j. So here there is another 50% chance of mistake. I think, in fact, I might have done a mistake. When you do a push forward with the rotation, it could be that the Radon-Nikodym derivative picks a minus, because, and those I never know. So this is subject to a plus minus, but the proof doesn't care. So let's not spend time on this. So the log is, as I advertised, is nice. It removes those. And so I'm only left in this relative entropy. I hope it will fit in this blackboard. So we're almost done. There is one remaining nice idea and we are done. So it's expectation of sum over I next to j. There is a beta in front, which will not play any role here. Beta times cosine theta I minus theta j minus cosine theta I minus theta j plus alpha psi I minus psi j. And maybe here there is a minus, but we don't care. So I need to understand the average value of this minus that. And what do I know? I know that this is small. This is the whole point of a spin wave. The gradients of the spin wave, not only they're locally small, but they're globally small in the sense that the sum of their gradient squared is small. So I want to use this, so we will do a Taylor expansion of this. So what do we have? We have cosine function. Maybe theta I minus theta j is here, and theta I plus, so that's theta I minus theta j plus alpha psi I minus psi j. So I will use one of the Taylor formula, I think it's Taylor Lagrange maybe, which says that this is beta sum from on all the nearest neighbor edges, and I have minus the derivative of cosine. Okay, so plus minus again, this will not be important. Sine theta I minus theta j times alpha psi I minus psi j plus or minus the second derivative, which will be again a cos. But this second derivative, I may need to take it at some intermediate point Tij, which could be anywhere between those, times alpha squared psi I minus psi j squared divided by 2. So I need to compute this. And now I am almost done. Why? Because this term, those are upper bounded by 1, and the sum over all the edges of this spin wave, we've seen that this is 1 over log n. So this is great. What is not great is this. This is bad because this is the sum over the, there is no absolute value, but still this sum could be large. We don't have a very good control on those. And those are typically of order 1, potentially. So here we could be stuck, but I don't know who got this idea, but I find it very nice. We are using Pfister inequality, and I will almost close with this. T alpha psi mu lambda n beta. So in total variation, this is less than the square root of 2 times the relative entropy of 1 with respect to this one. This didn't work, but there is another property of the relative entropy that we can use. It's the fact it is positive. So I can always add something else. And here I add in my proof, so it looks even less optimal. I add the relative entropy of mu lambda n beta relative to the push forward, and here I change sign. I push in the other direction my spins. And if I do this, the term that I added is a beta sum over I and j. But now whatever I add is the other one. And I have the same thing here, which then disappears. And then this side is the same. The second order of Taylor is the same one. This one does not disappear. I cannot cheat this much. And so I get that this whole thing is less than constant divided by log n. And so the total variation is less than 1 over square root of log n. So I think I will, well, I'm already late. So tomorrow I will finally start BKT. So I will tell you that despite the lack of long-range ordering for those systems that have a continuous symmetry, Berezinskii-Kosterlitz and Thouless in the early 70s, I will start with a small story. They discovered that there is nevertheless a phase transition, and it is as follows. At high temperature, the spins are exponentially uncorrelated. It's a bit like a white noise in space. So those are the pictures I had that were colored and very unrelated. But suddenly, at a critical point, they become power law decaying, which is something physicists in conformal field theory like very much, because power law means exponent, critical exponent, and lots of structure behind. So suddenly, the system still doesn't have any long-range order, but there is a whole line of critical points below the BKT critical value. So tomorrow, I will explain how the physicists came up with this phase transition. I will start the mathematical analysis. And it's a phase transition I really like. I did teach it a few years ago, and I liked it so much that I changed the research field almost, because this is a phase transition which is C infinity. So if you look at the free energy, it looks... The physicists managed to spot that there was an analyticity breaking. I don't know how they did, but it's C infinity, not analytic. The phase transition is due to vortices in the system, so I'll start explaining all this tomorrow. Thank you.
Are there any questions?
So like in percolation, the percolation measure is translational invariant, and when we consider any event which is also translational invariant, like the number of clusters, we had the 0-1 law. So here also, like if I consider this measure and I consider an event which is rotationally doesn't depend on the rotation, so will that also have probability 0 or 1?
So I think to have 0-1 laws of the type you mentioned, you could so there are ways to define translation invariant measures by starting not with this box of ZD but with a torus. And then you can let the torus go to infinity. Yet, it's not in percolation. What's completely obvious is that this product measure is ergodic. Here, it's not obvious that the measure is ergodic. So, so 0-1 law sort of requires that there is ergodicity behind. And if one takes the colored version that I had before, this green-blue red model, if you have 5 colors in dimension 2, it's known not to be ergodic at the critical point. So those are supposed to be all ergodic because of Mermin-Wagner, but this proof doesn't imply ergodicity. So supposedly yes, and then any events you would want to consider will have a 0-1 law, but ergodicity is a huge input to be proved to have this.
Yeah, I was wondering about the question maybe related to the pairs argument. Like if we consider two-dimensional XY model and we consider a boundary condition such that if we go along the boundary and the spin will go also clockwise, so there is a like vortex surrounding the box. Then if we make the box larger and larger and we look at the specific center, can we feel there's a small, very small vortex of the clockwise direction surrounding it?
Yes, it's a very good question. So I think the question you ask is, instead of having those Dirichlet type of boundary condition, can we impose something slowly varying here, such that there is a 2-pi monodromy? And so this is extremely interesting. In fact, if we let beta goes to infinity and look at the ground state of those, then this has to do with things Silvia Serfati has been doing, or what's the name? Ginzburg-Landau, right? So So if you do this, the ground state of this should potentially pick one vortex, potentially near the middle, and you will fill the vortex all the way to the middle. So there is a kind of symmetry breaking vortex type. But that would be true, but be difficult, I guess, at beta equals infinity, at t equals 0. As long as there is temperature, vortices will be created everywhere. This I will explain maybe next lecture, maybe in 2 lectures, because I was a bit slower than I thought. So there will be vortices created everywhere, which will screen off this boundary condition you are thinking about. At 0 temperature, this boundary condition will prevail conjecturally all the way to the bulk of the system, to the middle point or next to it. So yes, at 0 temperature, it's a very subtle effect.
Yeah, do you think there will be a phase transition up to some critical temperature?
I think this effect will disappear immediately as you turn on the temperature.
Thanks.
Thank you.
I'm wondering, like, to what extent can we play with the pilot argument, like, especially about, like, what type of symmetry groups can we have in the model so that this argument works?
Yes, so it's a very good question. So for each time you have a discrete symmetry group, this will work. Like if the target space is compact and you have a discrete symmetry group, it works perfectly well. If you have the z-valued model that I will spend some time on because it's a key figure of the proof of BKT, the symmetry group is z this time. But Peyer's argument will still work. It needs a bit of adaptation, but it still works. So every time there is a energy cost you need to play to go from one phase to another, Peyer's is very robust. It's only when there is a continuous interpolation that it really collapses.
Thank you. I have one as well. So it's a bit vague, but if you look at the Merlin-Wagner argument, and then you ask yourself what is the time for, say, a given spin to forget the orientation of the ones on the boundary. So it's not really defined, but I could define it as a mixing time or dynamic or something like this. Does the
the time along the dynamics, you mean?
No. I mean you explore dynamically from the outside, and then this is what you call the time.
Yes. So like the speed of convergence in total variation to the...
Yeah, my question is, is it possible to relate this mixing time, or whatever this is, to the minimum of the Dirichlet energy that you would pay for, like the optimal spin wave cost, or is it more complicated?
Yes, so it's a very good question. So the spin wave that I have built, the optimal one would be another constant divided by log m. So we did get the right speed of convergence for the spin wave. But we will see a theorem next time that at least the 2-point function decays much faster. It decays polynomially and not 1/√of log m. So it's a sign that it in fact mixes way faster than what so maybe vortices are helping but what we will prove is only the 2-point function. Here, this is the total variation distance. This is much stronger information. So I don't know if something remains. I guess no, but I think it would be I don't think it's known to have a polynomial decay of polynomial decay for total variations. I've never seen it.
Other questions? Okay, let's thank Christophe again.